Somewhere over the central Pacific Ocean, roughly 1,500 miles west of the California coastline, a corridor of moisture and wind stretching hundreds of miles across has been building over the past several days in a pattern that meteorologists at the National Weather Service and scientists at NOAA's Weather Prediction Center have been tracking with increasing attention. Not a hurricane, not a cyclone, not the kind of weather event that most Americans have a ready frame of reference for. What the satellite imagery shows is an atmospheric river, a phenomenon that is simultaneously one of the most consequential and one of the least understood weather systems in the world when it comes to what it means for the millions of people living in its path. And what the current models are showing is an atmospheric river of unusual size, unusual intensity, and an unusual forward motion that could direct enormous quantities of water directly into California at a time when significant portions of the state are particularly vulnerable to what a system like this one can deliver. This is what the monitoring data actually shows. What meteorologists at the National Weather Service forecast offices in San Francisco, Los Angeles, and Sacramento, along with scientists at the Scripps Institution of Oceanography at UC San Diego, have confirmed in their most recent advisories and forecast discussions. No lives have been reported lost yet because the event has not made landfall. But an atmospheric river of the scale and structure the instruments are currently tracking is not a normal weather event. It is a major water delivery system aimed at a coastline, and the real story of what happens when one of these systems strikes California at full strength is alarming enough without any embellishment at all. The technical measurement that scientists use to quantify the strength of an atmospheric river is called integrated vapor transport, or IVT, a value that captures how much water vapor the atmosphere is carrying through a column of air and how fast that air is moving. Atmospheric rivers are classified on a scale from 1 to 5 based on their IVT values and expected duration, with Category 1 and 2 events described as beneficial, delivering needed precipitation with manageable risks. Category 3 events can be beneficial or hazardous depending on where they hit and what conditions they find on arrival. Category 4 and 5 events are classified as hazardous to extreme. The system currently forming in the Central Pacific is producing IVT readings that have been tracking into the Category 4 range in recent model runs, with some ensemble members, the individual simulations within a broader forecast system, pushing values toward Category 5 territory depending on how the storm's structure evolves over the next 72 hours. The meteorologists publishing those forecasts are not hedging when they acknowledge that uncertainty. They genuinely do not yet know with confidence which end of that range the system will deliver when it reaches the coast. What they know is that the floor of the likely outcomes is already significant, and that the ceiling is the kind of event California experiences rarely and remembers for a very long time. The specific mechanism that makes this particular system more dangerous than its raw intensity number alone would suggest is its projected motion once it reaches the California coastline. Most atmospheric rivers that affect California enter from the northwest or west, push inland, deposit their moisture against the Sierra Nevada and coastal ranges, and then weaken as they advance eastward. The system currently tracking toward the coast is oriented in a way that the models consistently show making a much slower transit, a pattern that meteorologists call stalling or quasi-stationary behavior. When an atmospheric river stalls over a region rather than pushing through it, the total water delivered to any given location multiplies dramatically because the same corridor of moisture continues pumping precipitation over the same geography for hours or even days rather than the 12 to 24 hours of a more typical event. It is the difference between a powerful rainstorm moving through your area and a fire hose pointed directly at the same spot, left running. To understand why this matters most acutely for California right now, you have to understand the specific condition that makes the current timing more dangerous than the same atmospheric river arriving in a different season. Across significant stretches of the California landscape, in the watersheds above Los Angeles, in the foothills of the Sierra Nevada, along the transverse ranges of Southern California, there are thousands of acres of terrain that burned in wildfires over the past several years and have not yet fully recovered the vegetation cover that holds soil in place on steep slopes. Fire removes that vegetation. It also bakes a water-repellent layer into the top few millimeters of soil, a hydrophobic crust of burned organic material that causes heavy rainfall to run off the surface rather than soak in. Rain that would ordinarily be absorbed, slowed, and distributed gradually through root systems and ground cover instead moves across the surface as fast-moving, debris-laden runoff. On steep canyon slopes with loose burned soil above populated areas, that runoff becomes debris flow, a mixture of rock, mud, uprooted trees, and boulders that moves faster than a person can run, and that has, in past California storms, buried entire neighborhoods in the time it took residents to decide whether to act on the evacuation order they received. The most immediately life-threatening scenario that emergency managers in California are modeling in the days before this system's expected landfall is not the rain itself. It is what the rain does to the burned hillsides above populated canyons. In January of 2018, a debris flow in the Thomas Fire burn scar above Montecito, California, killed 23 people and destroyed or damaged hundreds of homes in the early morning darkness of a storm that produced less total rainfall than the system currently forming in the Pacific. The debris reached portions of Montecito in under 5 minutes from the moment it released on the hillside above the town. Many of the people who died had received an evacuation order the day before and had chosen to stay. That decision was not made carelessly. It was made by people who had been through evacuations before and weighed the inconvenience against a risk that was not yet visible to them. It is the same decision that communities across California's fire-scarred coastal mountains are now facing again. The infrastructure risks that sit below and beyond the burn scar zones are where the scale of this system's potential consequences expands from neighborhood level to regional. California's water management infrastructure, its dams, reservoirs, levees, and flood control channels, was largely built in the mid-20th century and engineered to handle the precipitation extremes that existed at the time of construction. The most vivid recent demonstration of what happens when that infrastructure meets the upper end of what an atmospheric river can produce is Oroville Dam in Butte County, north of Sacramento. At 770 feet, it remains the tallest dam in the United States. In February of 2017, a series of intense rain events filled Lake Oroville to capacity and overwhelmed the primary spillway, causing a catastrophic failure of the concrete structure. When engineers shifted to the emergency spillway, a structure that had never before been used, that too began to fail, threatening an uncontrolled release of water into the Feather River that prompted the mandatory evacuation of nearly 200,000 people downstream. The dam did not fail. The spillway was subsequently rebuilt at a cost exceeding $1 billion. But the event exposed, with a precision that no engineering study could replicate, how close California's most critical water infrastructure sits to its design limits under a major atmospheric river. The question of where those limits are in the event currently forming in the Pacific will be answered in the coming days. Here is the part of this story that NOAA and the National Weather Service want California residents to understand before the event makes landfall, not after. The danger in a stalling atmospheric river of this strength is not confined to a single dramatic moment of flood or debris flow. The danger accumulates. Every hour that the system sits over the same watershed adds to the soil saturation, raises the water level in rivers already carrying above normal flows, and increases the probability that slopes which held through the first 12 hours of rain will not hold through the next 12. The threshold between a dangerous event and a catastrophic one in this scenario is not a fixed line that forecasters can mark on a map. It shifts hour by hour as the ground saturates, as the rivers rise, and as the reservoir levels at Oroville, Folsom, and Shasta approach the capacity calculations that determine how much inflow can be managed before outflow becomes mandatory, and the rivers below them are required to carry water they were not engineered to receive simultaneously. To understand what makes atmospheric rivers capable of this kind of delivery, and why the system forming now is not simply a big storm that California needs to wait out, you have to spend a moment with what these systems actually are and where the water in them comes from, because the physics are genuinely remarkable, and they change what a 5-day forecast actually means. An atmospheric river is not a cloud. It is not a front. It is a narrow, concentrated ribbon of water vapor flowing through the mid-levels of the atmosphere, typically originating over the warm, tropical or subtropical Pacific Ocean, where solar heating evaporates enormous quantities of seawater into the air. That water vapor is then caught up in the atmospheric circulation and transported northward and eastward in a plume that can stretch for 2,000 miles in length while remaining only 200 to 300 miles wide. The total volume of water moving through a strong atmospheric river at any given moment rivals the average discharge of the Mississippi River. The difference is that the Mississippi carries its water on the surface, in a visible channel, where engineers have spent 150 years building infrastructure to manage it. An atmospheric river carries an equivalent quantity of water invisibly, miles above the ocean surface, in a form that drops all of it within hours once the right topographic conditions release it. Those conditions, in California, are the Sierra Nevada. The Sierra Nevada acts as a nearly perfect orographic trap for Pacific moisture. An atmospheric river that arrives at the California coast carrying vast quantities of tropical water vapor runs directly into mountains that rise in some places from sea level to over 14,000 feet within less than 100 miles. That rapid forced ascent extracts moisture from the atmosphere with exceptional efficiency, generating rainfall rates at foothill elevations that can exceed 2 inches per hour during the peak of a major event, while simultaneously depositing feet of snow at higher elevations. In a cold atmospheric river, the snow accumulation acts as a buffer. It holds water in the snowpack and releases it gradually through spring melt. The system currently tracking toward California is originating in tropical air masses warm enough to push the snow level substantially higher than a typical winter event, meaning more of Rainier's precipitation equivalent falls as rain rather than snow at elevations that would normally accumulate a snowpack. That removes the buffer. The water that falls as rain at 5,000 feet flows directly into rivers, rather than being stored in snow, and rivers that are already running high from earlier seasonal precipitation have limited remaining capacity to absorb it. The rivers that drain the western slope of the Sierra Nevada and deliver water to California's Central Valley, the Sacramento, the American, the Feather, the San Joaquin, run through a valley protected by an extensive network of levees, most of which were built or substantially reinforced across the mid-20th century. The Sacramento area levee system is one of the most extensive in the United States, protecting hundreds of thousands of acres of farmland and significant portions of the Sacramento metropolitan area from inundation. What engineers have documented in assessments published by the Army Corps of Engineers and the California Department of Water Resources is that meaningful portions of that levee system were built to standards that do not satisfy current hydrological or seismic safety criteria. A major atmospheric river event sustaining flows in the Sacramento and Feather rivers above certain threshold rates creates conditions in which levee failure, not as a theoretical worst case, but as a known, documented engineering probability, becomes a realistic concern. A levee failure protecting the Sacramento region in a major event would not be measured in affected neighborhoods, it would be measured in affected counties. There is a chapter of California's history that almost never appears in news coverage of atmospheric rivers, but that changes the scale of what these systems can mean for a landscape like this one. The most catastrophic flood in California's recorded history did not happen in the age of satellites and forecast models. It happened in the winter of 1861 and 1862, when a sequence of atmospheric rivers, large, intense, and arriving in rapid succession over several weeks, struck California and turned the entire Central Valley into a continuous inland sea. The Sacramento Valley was underwater for weeks. The state capital, then in Sacramento, became inaccessible. California's newly inaugurated governor, Leland Stanford, traveled to his own inauguration by rowboat through the city's flooded streets. An estimated 200,000 cattle drowned. A quarter of all taxable land in the state was submerged. 1 in 8 houses in California was destroyed or carried away entirely. The economic damage in modern terms would represent a disruption to the American economy with no precedent in the recorded history of natural disasters in the United States. The USGS studied what would happen if a similar sequence of atmospheric rivers struck modern California. The scenario they constructed, published under the name rainstorm, a deliberate fusion of Arkansas River flooding and the biblical ark, projected that an 1862 scale atmospheric river sequence hitting the state today would displace an estimated 1.5 million people from their homes, flood the Central Valley on a scale not seen in living memory, and produce damage exceeding $750 billion. More than any projected earthquake scenario for California. More than the modeled cost of a full San Andreas fault rupture through greater Los Angeles. Rainstorm is not a theoretical extreme engineered to produce alarming projections. It is a paleoclimatologically grounded assessment of an event type that the geological and sediment record confirms has occurred in California multiple times in the past 2,000 years, and that has not become less likely as the atmosphere's baseline moisture content has risen. The climate connection to what is forming in the Pacific right now is one that researchers are careful to articulate precisely. Atmospheric rivers are not a new invention of a warming climate. They have always existed and have always delivered California's most extreme precipitation. What the research, including the foundational work published by F. Martin Ralph at the Scripps Institution of Oceanography, who developed and refined the current 1 to 5 atmospheric river classification scale now used by NOAA, demonstrates is that a warming atmosphere holds more water vapor, and more water vapor means more potential moisture transport per event. The same synoptic weather pattern that produced a Category 3 atmospheric river in the mid-20th century may now produce a Category 4 event simply because the air masses involved are carrying a higher moisture load than they would have carried 50 years ago. The distribution of atmospheric river intensity has shifted. The mean has changed, and the upper tail, the Category 4 and 5 events like the one currently forming, has shifted with it. California has experienced the consequences of that shift in consecutive heavy rain seasons that each broke records set in previous consecutive heavy rain seasons. The forecasting and monitoring capability tracking this specific system is among the most sophisticated infrastructure of its kind in the world. NOAA operates an atmospheric river reconnaissance program, known within the meteorological community as AR-RECON, in which specially instrumented NOAA and Air Force Reserve aircraft fly directly into atmospheric river systems over the Pacific Ocean before they reach the California coast, releasing dropsondes at regular intervals that measure temperature, humidity, and wind speed throughout the atmospheric column inside the event, and transmit that data directly to the numerical forecast models that predict where and how hard the system will hit. The improvements in forecast accuracy that AR-RECON flights produce are not marginal. Studies comparing forecast performance with and without AR-RECON data have shown measurable reductions in forecast error across the models used by the National Weather Service, improvements that translate into better calibrated warnings, more accurately timed evacuation orders, and more precisely targeted pre-positioning of emergency personnel and equipment. The meteorologists at Weather Prediction Center in College Park, Maryland, and at regional National Weather Service forecast offices across California are drawing on AR-RECON data from recent reconnaissance flights as they issue the advisories that will guide California's response in the coming days. For the communities sitting in flood zones, burn-scar watersheds, and aging levee corridors across California, the farm workers in the San Joaquin Valley living in housing that sits in the shadow of levee grades, the families and communities east of Los Angeles who rebuilt after fire and are now watching storm tracks, the residents along the Russian River in Guerneville, who have been through enough atmospheric river floods to keep their most valuable possessions on upper floors as a matter of seasonal habit. The days before a major system's landfall carry a very specific weight, not abstract fear, the concrete, practiced weight of people who have been through a major flooding or debris flow event before, who know exactly what it looks and sounds and smells like, and who are already making the calculation of whether this is the time they leave before the mandatory order comes, or whether they wait to see if the forecast tracks the way the forecasters believe it will. Emergency managers across California are urging residents in the highest risk zones not to wait for that question to answer itself. A burn-scar debris flow can materialize in 20 to 30 minutes of heavy rainfall, with no additional warning beyond the rain itself. The lesson that Montecito wrote into California's institutional memory in January 2018 is that by the time a debris flow is visible, the window to act has often already closed. Atmospheric rivers cannot be stopped. They cannot be redirected. They have been delivering water to the California landscape since long before California was California, and the mechanisms that generate them will continue doing so regardless of any human decision made in the hours before landfall. What can be controlled is how well the human response system, the reservoir pre-releases that create capacity for incoming flows, the burn-scar evacuation orders issued before the first heavy rain, the levee patrol deployments that can detect weakness before it becomes failure, the public warnings calibrated to what the AR-RECON data actually shows rather than what emergency managers wish it showed, is positioned before the water arrives. Keep watching the National Weather Service advisories for your specific county as the system approaches and the forecast cone narrows. Keep watching the reservoir inflow rates at Oroville and Folsom. Keep watching the USGS landslide hazard assessments, which will be updated as soil saturation levels rise across burn-scar areas. And if you live below a burn scar, in a flood-prone valley, or beside a river that has already run high this season, take the current forecast seriously enough to have a plan that does not depend on receiving more warning time than this storm has any intention of providing. The water is already in the atmosphere. It has been building for days. The only question still being answered by the models is exactly where it lands, and whether the people in its path decided, before the rain began, that this time was the time to be ready.